What does it mean for something to be theoretical? What does it mean for something to be a theory? Not necessarily not real, but okay, it has to be proven, right? Okay, it's not necessarily proven. Okay, a theory is like, hey, this is how we think it will work, but does it always work out that way? No, theories are not always true. Theories do not always come to be factual, okay? But they are thought to be true, okay? It makes sense in our mind, kind of a thing. That's typically what a theory is, okay? If we're talking about theoretical, that's just saying, hey, this is based upon a theory. So theoretical probability is saying, hey, this is how we expect things to go. It's the probability. Probability is the measure of how likely an event is to occur. I'm saying, hey, how likely is this to happen? So we have the set of all possible outcomes from some event, and that's called the sample space. For equally likely outcomes, the theoretically probability of an event is P of E. Probability is the P of event E, would be how you read that. And it's the ratio of the number of favorable outcomes to the number of total outcomes possible. And we'll explain that in a moment. So here's an example, okay, of what we call a simple event. A simple event is just one thing happening. So you have a jar that contains 32 red marbles, 28 blue marbles. You want to know what's the probability or likelihood that you randomly draw a red marble. So you aren't looking, you pull out a red marble. What are the odds? Well, how many red marbles are there? 32. How many total marbles are there? 60. So 32 out of 60 of the marbles are red, right? Now, do you have an equal chance to grab a red or, is it any more likely that you grab one marble more than another as you're not looking, like kind of a thing? Not even just based upon color, but will they feel any different? Like, would you know they're different without looking at them? No, so when your hand's in the bag, do you know what you're grabbing? No, okay? You're just grabbing one, right? So, when we say, what are the odds to grab a red marble, what do we say? It's more likely or less likely that it's red than blue? More likely that it's red, right? Because, why? There's more of them, right? There's more red ones. So we say the odds or the probability or likelihood that we draw a red marble is 32 out of 60 because there's 32 marbles of the 60 are red. Now, can we reduce this fraction? Yeah, what number goes both into 32 and 60? 2 does? Is there even a bigger one? 4. So it becomes 8 over, does anyone know? 15. So the odds are 8 in 15 that you'll get it. That means, theoretically speaking, if you draw 15 marbles out, how many of them should be red? 8. Now, will that always work out to be the case? No, it won't. Okay? But that's the probability of it, okay? That's like saying, if I flip a coin twice, what should I get total? I should get one what and one what? I should get one heads and one tails if I flip a coin twice, right? Because it's equal likelihood to get heads or tails as long as it's not like a, weighted coin or something like that. Now, so if I flip this twice, okay, I got heads. If I flip it again, I did get tails. Now, is that going to happen every time that I get one of each, one right after the other? No, okay? So that's the difference between theoretical and what we call experimental probability. Experimental is what happens when you actually conduct an experiment. So this right here, all talking about theoretical, what are the odds of this happening, okay? Number 2, a letter in the word restoration is randomly selected. So it's like you take all those letters, you put them on a piece of paper in a hat. You pull one out. What's the probability of selecting a vowel? Well, what do we have to figure out first?
How many total letters there are.
How many total letters there are, and what else do we have to figure out? How many vowels there are, okay? So how many total letters are there? Okay, there's 11 letters, and you need to count repeats, right? Because they'd be put in there twice. So not only repeat, but repeat too.
5 vowels.
And there's 5 vowels? Okay, I agree with 5. So can this reduce? No, so what are the odds you grab a vowel? 5 out of 11. So if you grab one letter, are you more likely to get a vowel or a consonant right away? You're more likely to get a consonant, right? Because there's more of them. Just barely, though, right? All right. Questions on those first two? Okay. I really like this. I think it's very applicable. All right. A day in the month of January is randomly selected. What is the probability of selecting a prime number? Prime number. Well, how many days does January have? 31. So it's going to be over 31. So now I have to figure out how many prime numbers are there in the first 31 numbers. Okay. Well, prime numbers, we define that as a number bigger than 1 that only factors are 1 in itself. So is 1 prime then according to that definition? No, because it has to be bigger than 1. So is 2 prime?
Yeah.
Okay, so we have 2. Is 3 prime? Yeah. Is 4? No. Is 5? Yeah. Is 6? No. Is 7? Is 8? No. Is 9? No. Is 10? No. Is 11? 12? 13? 14? 15? 16? 17? 18? 19?
Yes.
19, yeah, that's prime. Okay. 20? 21? 22? 23? Yep. 24, haha. 25, haha. 26? 26? No, 2 goes into it. 27? 3 and 9. Ooh. 28. 29. Yeah, that's prime. 30. Okay, 31. 31's prime. That's all of our prime numbers from 1 to 31. Oh, okay. How many are there? 11 of them. So that means 11 of these 31 are prime. So what's the probability of selecting a prime number? 11 over 31. So is it more likely you pick a prime number or a non-prime number, a composite number? It's more likely you pick a composite number, right? Okay. 2 dice are rolled. What's the probability that the sum of the 2 dice on the roll is at least 9? There's lots of games that incorporate dice here. So, could you use this kind of knowledge in your head to try and actually figure out what a better decision during a game would be? Should I go for this or that? Well, is it likely for me to get this dice roll or not? Does that make sense? Okay. What is the probability of drawing a heart or a club from a standard deck of cards? Well, a standard deck of cards has how many cards? 52 cards, right? And in the standard deck of cards, how many suits are there?
4.
4. So how many cards are there per suit?
13.
13, right? There's ace through 10 as well as the face cards, right? Jack, queen, king. Okay? So there's 13 cards per suit. Now the suits are hearts, clubs, spades, and diamonds. So, hearts or a club. How many cards would be either a heart or a club then? 26 of them would be either a heart or a club, right? 13 for hearts, 13 for clubs. Does that make sense? How we get that or no? I'm seeing a lot of blank stares.
I don't get it because I don't know hearts or clubs or cards. I don't know the number. Okay, so heart.
When you're a math teacher, you gotta have dice, cards, and coins in your desk, okay? Isaac also just has them, okay? So in a deck of cards, there's different suits. So here would be the 4 different suits. Spades, clubs, diamonds, and hearts. So there's 52 total cards. Each suit has the same types of cards. They all have an ace, which is a 1 most of the time. 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 right there. 1 through 10. Then they have these face cards. A jack, a queen, and a king. Which are obviously kind of like 11, 12, 13. So each suit would have 13 cards. So if there's 13 hearts, 13, what was the other one here? Clubs. How many would that give us total between hearts and clubs? 26. Does that make more sense? Awesome. So now could we reduce that? Yeah, what does this reduce to? 1/2. 26 is half 52. Now, that makes sense. What are the odds we get 2 suits versus the other 2 suits? 50-50 shot. Exactly even odds. 50-50 shot. Questions on that? All right. Let's go ahead and we're going to skip 6. Let's talk about the complement of event. Complement would be the other part of something in this case. Not like you're just being nice to somebody, it'd be the other part of something. The complement of an event is the probability of the event not happening. Since the sum of all probabilities in the sample space is 1, aka if you add up all the odds of everything, you should get a total of 1. Meaning like 1% of it, like 100% chance of something happening. If you ever have all the sample space adding up to more than 1, you did something wrong. The probability of an event not happening, so the probability of an event happening was just P parentheses E. Probability of an event not happening is going to be this little squiggly E. That squiggly is going to mean not. Okay? So it's going to be 1 minus the probability of it happening. So if you take 1 and you subtract the probability of an event happening, you get how likely it is for it to not happen. Let me put that into example for something we just did. With the dice, we said, what's the probability we get at least 9 on 2 dice roll? 5/18 was the probability we get at least 9. So what's the probability we get less than 9? Well, you could do 1 minus 5/18. 1 minus the odds that we get at least 9 would be the odds that we don't get 9. We get less than 9. So 1, we'd want to make 18/18 to make it common denominators. And so the odds that you don't get at least 9, so you get below 9, would be 13/18. Does that make sense? So that you have to add up to one full number to be below 9 as well as being at or above 9? Because that has to be all of our options here. So in probability 1 is when we have every option accounted for. 1's like 100% of options in probability, okay? So the probability that it will snow tomorrow is 7 out of 20. So what's the probability it won't snow? 13 out of 20. And Abby, what was the math you did there?
7 to 20 is 13, and then just put it over 20. It didn't really happen.
Okay, but what did you end up having to add them up to? Like, what did you add 7 and 13 up to? 20. Because 20 divided by 20 is 1. So really what was happening behind the scenes in your head was you took saying, hey, I know I need to get 7/20 to add up to 1. So if you take 1 minus 7/20, and 1's secretly going to be 20/20, because that's the same thing to have 20 divided by 20 be 1, right? Does that make sense? Anything divided by itself is 1. 20 minus 7 is 13. So there's a 13/20 chance that it will not snow. Questions on that? All right. Music?
Yeah.
Oh, it's great. Yeah. A month of the year is randomly selected. What is the probability of getting a month that does not begin with the letter A? A month that does not begin with the letter A. So there's a couple ways you could do this.
There's only 2 months that we have, right? April, August.
Okay? Yeah, there's two ways we could do it. We could take 1 and subtract however many months begin with the letter A, which Abby just said. Well, there's 2. It's April and August. So you take 1, the entire year, which would be like 12 out of 12 months. Subtract 2 out of the 12 months. So that'd be 12/12, which would be 10 out of 12, which gives us 5/6. The other way you could do it, could you just add up all the months that don't start with A? Sure, you could say, okay, January, February, March, May, June, July, September, October, November. Oh, that's 10 of them. And go from there. Does that make sense how you kind of go about it both ways? So you can subtract what you know, or you can add up another option. Okay. 10. Let's skip number 9. 10. 2 dice are rolled. What is the probability of not getting doubles? Well, we talked about how with dice, there were 36 total options, right? So out of these 36 options, how many of them would produce doubles? Let's think about this. When I was going through this and I counted through all my ones, how many of them were doubles? 1. When I went through all my 2s on one die, how many of them were doubles? 1. So how many doubles do we think there's going to be total? 6 total options, okay? They're both 1s, they're both 2s, they're both 3s, they're both... So, continuing on. So, the probability that one of them is that they're doubles is 6 out of 36, correct? Which would reduce to 1/6. So how would you figure out the probability of it not being doubles? Subtract it from 1. Do 1 minus that. And we could say 1 is secretly 36 over 36. And you say, hey, we get 30 over 36. Okay, it can reduce to 15 over 18, but it can also reduce more. Divide by 6 and go to 5 over 6. So is it more likely you don't get doubles or more likely you do get doubles? It's more likely you don't get doubles, right? By quite a bit. 5 times as likely you don't get doubles than you do.
Could you tell me what the answer for 9 was? Do you have that?
5 over 18.
You didn't just do that like in your head?
No, I have it written down.
It was 5 over.
5 over 8. Did I say 5 over 18?
Yeah.
5 over 8.
Oh, wait, 5 over 8. That's right.
On number 9. Yep. It simplifies.
So number 16.
All right. Let's continue on. Let's talk about compound events. So compound is going to be the opposite of simple. We said simple events was one event happening. Compound events, probability of 2 or more simple events. So you're compounding them. So we have 2 different types. We have independent and dependent. Independent events, when the outcome of one event does not affect the outcome of the other. Dependent is going to be when the probability or the outcome of one does affect the other. So in independent events, take the probability of A and B happening, event A and B happening. You take probability of A happening times the probability of B happening. You multiply the 2 probabilities. And that's how you get the probability of them both happening. For dependent events, where one depends on the other, you do the probability of A happening times the probability of B happening, but it's after A occurred. I'll talk about that. We'll talk about independent before we talk about dependent, though. Number 11 says, a die is rolled 3 times. What's the probability of getting 1s on each roll? So I roll it the first time. What's my probability of getting a 1? 1 out of 6. Now the second time I go to roll it, does my first roll impact my second roll at all? No, it's equal odds either time. So what are my odds of getting a 1 on that roll? 1 out of 6. And what are my odds of getting a 1 on the last roll? 1 out of 6. They don't affect each other at all. So I multiply all these together when it says getting it on each. Well, I have to multiply them together to get the probability of getting a 1 on each roll. So to get a 1 3 times in a row is going to be 1 over 6 times 6 times 6, which is 1 over 216. Is that very likely to get the same number 3 times in a row on a die? No, it can happen. I mean, it's there. It can happen. Right now, when I rolled, I got it once. So those are events that did not depend on each other. Number 12. A coin is tossed, then a day of the week is selected. Do those relate to each other at all? Would they depend on each other at all? Not even close. Okay? So what's the probability of getting tails, then a day starting with the letter T? So what's the probability of the first event happening? 1/2. What's the probability of that second event happening? A day of the week starting with the letter T. 2 out of 7. And you multiply those together. 1/2 times 2 over 7. Now, could we do cross simplifying here? Yeah, we can simplify that 2 and the 1. Or the 2 and the 2, excuse me, to 1 and 1. So what are the odds of these both happening together? 1 out of 7. Once again, that's because they're independent. Questions on that? All right, we're going to do a couple of these. Not all 4 of them, though. A bag contains 8 red crayons, 14 purple crayons, 6 yellow crayons, and 4 green crayons. If you don't say crayon that way, you're wrong, okay? No, who just said crayon? You're getting kicked out of class, okay? You're going to fail the final, I guarantee it now, okay? A crayon, that's how it's spelled and pronounced, guys, is selected, replaced, so it's put back in the bag, then another is selected. So if I put it back in the bag after I select it, will that impact my next choice at all? No, because it's back in the bag. We started with the same amount. Now, what if I take it out and I keep it out? Will that impact my next choice? Yeah, because I can't draw that one anymore, can I? If I take a card, will that make it so there's less of that suit and that card in the deck? Yeah, so when I go to take another one, is it less likely I get a king? Yeah, because there's one less of them in the deck. But if I put it back, is it any less likely now? No. So, what's the probability of getting a purple, then a yellow? So we have to figure out first, what's the probability of getting a purple crayon? Well, how many purple crayons are there? 14. And how many total crayons are there? 32. So the first one is 14 over 32. Now, for my next one, what's the probability of getting a yellow crayon? 6 over 32, because there's still 32 crayons in the bag, because I put the one back, the purple one I grabbed the first time. So we multiply them together, and we can reduce here, right? I would advise it. First, I'd reduce inside of the own fraction. So 14 and 32, what can that reduce to? 7 over something. 7/16. What can 6 and 32 reduce to?
1 over 5.
3 and 16. Can we cross reduce any more? No, we can't. So you do multiply straight across. 7 times 3 is 91. 16 times 16, you could use your calculator, but it's 256. So what are the odds you get a purple, then a yellow? 21 out of 256. Is that pretty good odds? Not at all. Not at all.
Cards say Carnival.
Yeah, like the cruise line.
Have you been on a cruise before?
I have, yeah. My parents love them. All right. Any question on that, guys? Okay, we're actually going to skip 14, 15, and 16 for now. And we're going to move on to dependent events, because they're pretty similar.
Are they not good enough?
Dependent events. So these are going to depend on each other. So using the same example as above, same number of crayons, same colors, all that. But once a crayon is selected, what happens? It's not replaced. So what are the odds of getting a yellow, then a red? So what are the odds of me drawing a yellow one first? 6 over 32. Now after I grab a yellow one, how many crayons are left? 31. Now are there still all of the red ones in there? Yeah, so there's all 8 red ones in there. So you have 6 over 32 and 8 over 31. Does that make sense how we got that or no? Okay. So once again, it's because it's dependent, because there's not replacement right now. Ava, you okay? Is it making sense or no? Okay. All right. 6 and 32 we talked about, that reduces to 3 and 16. Can we still cross simplify though here?
Yeah.
Oh, heck yeah. 16 and 8. 2 and 1. Multiply straight across. 3 times 1 is 3. What's 2 times 31? 62. So the odds now are 3 over 62. Not great. Question on that. Okay. Let's do number 19. The probability of getting 2 reds. What's the probability of getting a red with your first one? 8 over 32. There's 8 reds and there's 32 crayons. What's the probability on the next one, though? If you take a red out, how many reds are there going to be left? 7 out of 31. So notice, because we assumed we took a red out of the first one here, we have to reduce the number of reds, as well as the number of crayons. Questions on the setup? Okay, this math, 8 and 32 reduce quite nicely to 1 and 4. 7 and 31 do not reduce. They're both prime. 1 times 7 is 7. 4 times 31 is 124. And that's your likelihood of getting 2 reds in a row. Not very likely. Questions of that?